Hello, everyone. This is going to be our first, two-thirds of our notes on 5.2, our sum and difference formulas. So we're going to start with kind of a proof by contradiction here. We know a little bit about our unit circle. I have one set up over here we'll reference throughout the course of our lesson. And really, we're just looking, is this statement true? Is the sine of 90 the same as the sine of 60 plus the sine of 30? Well, I'm going to scroll back over to my unit circle. I know that the y values on my unit circle correspond to the sine, and the x value is the cosine. So I'm using my y values here. I can see that the y coordinate at 90 degrees is 1, at 60 degrees is root 3 over 2, and at 30 degrees is 1/2. So what this statement would imply, if it were true, would be that 1 equals root 3 over 2 plus 1/2. Well, we know that's not true. In other words, our trig functions, sine, cosine, tangent, they're reciprocal functions. They don't distribute, right? We can't distribute the sine function to a pair of angles inside the parentheses. We need another method. So we have sum and difference formulas. So I'm going to start by giving us the sine, sum, and difference formula. That is going to be sine of our first angle times the cosine of our second angle plus the sine of our second angle times the cosine of the first. Additionally, our sine difference formula is going to behave very similarly. The only thing that's going to be different is the sign in the middle. So here I'll have sine B, cosine A. So if I want to find the sine of a sum of two angles or the difference of two angles, I need to use these two formulas. One thing that I've used over the years just as a memory tool, right? The sine matches with the sine, sum, and difference, right? So if I have a addition or a subtraction, well, the addition or subtraction sign will also show up in their formulas. The other case is our cosine. This one will behave similar, but not exactly the same. It is going to be the cosine of my first angle times the cosine of the second minus the sine of the first angle times the sine of the second. And as you might imagine, the cosine difference formula is mostly the same. Sorry, that's an A. Except the sign changes when we switch from addition to subtraction. Unlike our sine sum formulas, the sign is not matching here. You can see that the signs must be opposite with our cosine sum factors. One other thing that I've thought of over the years is that cosine is, coupled up, cosine, sine, sine. Cosine is coupled up here again. Just a mnemonic, just a way that is stuck in my brain over the years. So these are our formulas, trying to get them all on the page here. They're a little bit lengthy looking formulas, but these formulas will allow us to find exact values of angles, right? Up until this point, the only exact trig functions that we were able to find came from our unit circle. The sine and cosine sum formulas are going to help us out. We're going to add to our list. Basically, we're adding to the number and type of problems that we can evaluate without the use of a calculator. So let's look at an example. Here we have the cosine of 75 degrees, and 75 degrees, would be located right about here on our unit circle. However, it's not given. So what we want to do is we want to choose two angles that we do know and add or subtract them. I'm going to use 45 degrees and 30 degrees. I like to choose the smallest angles I can, angles that are positive whenever I can, just as I set this up. So now I've rewritten 75 as the sum of 45 and 30. Now I'm going to use my cosine excuse me, I'm going to use my cosine sum formula. That tells me that's going to be the cosine of 45 degrees times the cosine of 30 degrees minus the sine of 45 degrees times the sine of 30 degrees. Now, the reason we like these values is because they are right on our unit circle, just from our first quadrant. So the cosine of 45 degrees, we know that that's going to be root 2 over 2. The cosine of 30 degrees, we're just getting the x value from our 30-degree angle, root 3 over 2. From that, we're going to subtract the product of root 2 over 2 and 1/2. Again, these values coming directly from our unit circle. And once we simplify, we get root 6 minus root 2 all over 4. And that is our simplified form for the cosine of 75 degrees. Just a piece of advice, I have this unit circle here marked up. And specifically, I've marked up radian values, right? So what you'll notice about all these radian values is I've chosen a least common multiple, a greatest common factor in the denominator, that will give me, least common multiple of our denominators that will give me a common denominator. Because when we move into radians, like we do on example 2, we have to find angles that aren't on our unit circle, and in order to do that, we're going to have some different values. So if I want to create pi over 12, what I would do is I'm going to take 3 pi over 2 minus 2 pi over 2. Now, in reality, I'm going to use the sine of pi over 4 minus pi over 6. But just by writing down all of my radian angles in with a base of 12, it just gets me a little bit closer to where I want to be. So I'm going to use pi over 4 and pi over 6. And now I'm going to use my sine sum formula. That's going to get me the sine of pi over 4 times the cosine of pi over 6, minus the sine of pi over 6 times the cosine of pi over 4. And now I'm just evaluating. I'm going to get root 2 over 2. Try that again. And root 3 over 2 minus 1/2 times root 2 over 2. And what we'll find when we simplify this down, we'll get root 6 minus root 2 all over 4. If you're wondering, does that number seem familiar? It absolutely does. If we were to evaluate this, convert this, this is really the sine of 15 degrees. So it makes, some sort of logical sense that the cosine of an angle is identical to the sine of its complement, right? This makes sense that we got the same answer for these two. All right, so I'd like you to try the next two on your own. I'm going to give you just one piece of advice here. I'm going to rewrite cosecant of negative 15 degrees as the sine of negative 15 degrees. 1 over the sine of negative 15 degrees. Generally speaking, we don't like to use our reciprocal functions. We'd rather use their the main three, sine, cosine, and tangent, and get away from those reciprocals. So I'm going to pause the video, and then I'll share my work with you, so you can check your work against mine. All right, let's take a look at these couple problems. So for cosine of negative 11 pi over 12, again, I went to my unit circle using those common denominators of 12 just to try to make sense of this negative 11 pi over 12. I decided that negative 2 pi over 3, which would get me negative 8 pi over 12. And then from that, I'm subtracting pi over 4. That gets me my negative 11. So once I have my cosine difference set up, I am applying my formula. You can see there on my second step. and then I'm evaluating. Again, you're going to notice these similar values show up, different versions of root 2s and root 6s being added and subtracted. This all makes sense if we look at the reference angles that we've been finding here. They are either 75 degrees or 15 degrees, so it has some logic to it why we might end up in similar places. Moving on to number 4, this is a cosecant sum or difference problem. I used 1 over the sine of 30 degrees minus 45. So let me just mark this so you can see which step is which. So I have 3 steps here. I first rewrote the cosecant as 1 over sine, and then I wrote the sine as a difference, 30 minus 45. Here I'm looking at my sine difference formula, and then on this step down at the bottom, I'm evaluating. A little bit messy. We end up with a complex fraction, 1 over root 2 minus 6 all over 4. So I multiply by the reciprocal. And then what you see in blue here is just rationalizing my denominator, multiplying by the conjugate of root 2 minus root 6. And when it's all simplified, we end up there with negative root 2, either minus root 6 without parentheses or negative everything in parentheses, root 2 plus root 6. So there's another couple type of problems that we're going to see here. What you notice on these first 4, we're using values that show up on the unit circle. And because we're using values that show up on the unit circle, a lot of the numbers that we see just get repetitive. So here's a situation where we'll have some different values in our answer. So I have 2 pieces of information in this problem. I have one angle, we'll call it A here. It is in the first quadrant, so I'm going to sketch that angle A. And this angle has a cosine of 3/5. So as we're going here, we're going to have to sketch these triangles. This is a right triangle, so I can also write in my third side. I have a second triangle that I'm going to have to construct. That triangle exists in the second quadrant. So I'm going to sketch that. Let me just clean that up here for a moment. And this angle, angle B, has a cosine of negative 12 divided by 13. That's also a Pythagorean triple, so I can plug in that third side. Well, now what do they actually want us to find? They want us to find the sine of A plus B. So we need to use our sine sum formula. Sine of A, cosine of B, plus sine of B, cosine A. Well, all those values are going to come directly from our triangles. I'll try to color code them so you can see where they're coming from. The sine of A is 4/5, and the cosine of A, which they told us in the problem, was 3/5. The cosine of B, negative 12/13, and the sine of B is 5/13. Oh, this just becomes a simplify problem here. I have negative 48 plus 15. That's going to get me negative 33, and I already have a common denominator of 65. So what did we actually find? What we found here was the sine of this angle here plus that angle there. What do we know if it's negative? That it would have ended up somewhere in the third or fourth quadrant, but other than that, we don't have a ton of information. So there is one more problem like this, number 6, which doesn't look exactly the same, but because we're using our trig inverse functions, everybody's favorite, we're going to actually need to think about some intervals where these angles could exist. So what this is really asking me is to find the sine of 2 angles added together. Those 2 angles, well, the first one has a cosine of 1/2. Sorry, that would just be root 3. And then the second angle here has a sine of 3/5. Now, as I drew these, they both ended up in the first quadrant. Remember, with cosine and sine, each of these have, inverse cosine and inverse sine. Each of these have specific intervals over which they exist. Cosine goes from 0 to pi, and sine negative pi over 2 to positive pi over 2. So if I have a positive cosine and a positive sine, I must exist in the first quadrant. So same idea here. We're going to use our sine sum formula. Let's label these. Let's label this as A and this as B. So what I'm really finding is the sine of A times the cosine of B plus sine of B. So let's see, sine of B, cosine of A. Well, we have our triangles right there, so we can use those in our right triangle trig. Sine of A, root 3 over 2. Cosine of B is 4/5. Sine of B is going to be 3/5. And finally, cosine of A is going to be 1/2. Well, now all I have to do is simplify here. I'm going to have 4 root 3 plus 3 all over 10. Always worthwhile to, after we get through all that, what did we really find? If I wanted to find the sine of these two angles given in the problem, two angles that are given through inverse trig, an angle whose cosine is 1/2 and an angle whose sine is 3/5, well, we can find the sine of that sum, and we found it to be 4 root 3 plus 3 all over 10. There are two proofs here. I do think they're pretty straightforward. I definitely think you should try these on your own. I'm going to pause the video here and just work them out, and you'll be able to check your work against mine. But again, I strongly encourage you to try these on your own first. So both of these proofs end up being pretty simple. Thinking about how to choose which side on the number 7, well, there's not much going on the right-hand side. It's just cosine. Left-hand side, we have moves that we can make. So the moves I made here, let me just number them so you can kind of track along with me. That first one, that's our given information. And then our second step here, I just expanded this using our sine difference formula. Our third step, I plugged in and evaluated what I could. Right, I know that the sine of pi over 2 is 1, cosine of pi over 2 is 0. And just through multiplying and simplifying my last step, I find that all of what I see on the left is the same as cosine, which is what I was looking for. Proof done. And then on number 8, again, the left-hand side's more complicated. Adding and subtracting is more complicated than multiplying. So we expand both of those cosine, the cosine sum and the difference, and we end up with some like terms on step 2. So that what you can see in blue there is actually part of our third step. We are adding like terms. We have a cosine A times cosine B. One's positive and one's negative, so we add those together to get 0. And then we add our like terms of sine A, sine B together to get 2 times sine A, sine B. Again, that's what we were going for. We got where we were hoping, and we are done. So that wraps up this lesson. We'll move on to tangent sum in our next lesson. Nice work, everyone.